In the next few videos, we're going to talk about finitely generated abelian groups. So let G1, G2, and so on up to GR be groups. They don't have to be abelian. Then we define the direct product of these groups to be a new group. It's denoted G1 times G2 and so forth times GR. And this is a group. And I have to tell you then what its underlying set is. It's a set of ordered R tuples, where R is the number of groups. And this is called the Cartesian product of these sets. And the group operation is component-wise. Let's do an example to see what this all means. So I have two groups, Z mod 3 and Z mod 4. Remember, Z mod 3 is the numbers 0, 1, and 2. And the group structure is addition. In other words, for example, 2 plus 2 is 4, but then mod 3 is equal to 1. So in this group, Z3, 2 plus 2 is 1. Similarly, Z4 is 0, 1, 2, 3 as the elements of the set, and then the group operation once again is addition. Okay, and then the Cartesian product of Z3 times Z4 is the set of ordered pairs, where R is now equal to 2, so two tuples, or ordered pairs. So we take a pair of numbers, one from Z3, the other from Z4, and so here is all the elements of Z3 times Z4. It's 12 of them. Even though we use the symbol times, we're not multiplying the numbers in Z3 with the numbers in Z4. And anyway, we see that Z3 times Z4 has 12 elements. Maybe that's a little bit the reason why we use this multiplication notation. Okay, and here I've listed all 12 elements. And then let's explain this sentence here that the group operation is component-wise. So say I have two elements in Z3 and Z4. Let's take 1, 1 and 2, 1. Then the group operation, so if I want to add them, well, the group operation is denoted with an addition sign. And I just add them component-wise. In other words, I take the first component 1 and the first component here, which is 2, add them, so that's 3. Add the second components, 1 plus 1 is 2. And now in mod 3 land, Z mod 3, 3 is the same as 0, so 3 comma 2 is equal to 0 comma 2. So that's our result. If I take this number or element 1 comma 1, add it to 2 comma 1, I get the answer of 0 comma 2. That's the group operation on Z3 times Z4. Let's do another example. If I want to add 2 comma 2 to itself, I add in the ring of integers 4 comma 4, and then 4 is the same as 1 in mod 3 land, and 0 in mod 4 land. And so so 2 comma 2 plus 2 comma 2 is 1 comma 0. And we can easily see that this is an abelian group because Z3 and Z4 were abelian groups. Abelian again means commutative. In other words, A plus B equals B plus C. Let's ask a simple question. What is the order of the element 1 comma 2 in this new group we have, Z3 times Z4? To solve that, well, we find that the order of 1 in Z3 is 3, because that's how many times we have to apply the group, add the group element to itself to get back the identity element, which is 0. And then the order of 2 in Z4 is 2, because that's the number of times we have to add 2 to itself to get 0 in mod 4 land. And so we found the order of each one of these elements, 1 and the order of 2, separately. And then to find the order of this combined element, 1 comma 2, this ordered pair, the trick is to take the least common multiple of the orders that we found, the orders of the individual elements in the individual factors of the direct product group. So the least common multiple of 3 and 2 is 6, and so that's what the order of 1 and 2 is. Now you can check this directly by adding 1 comma 2 to itself, 1 times 2 times 3 times and so forth, and eventually you'll get to 0 comma 0 only after you've added 1 comma 2 to itself 6 times. And if you think about it, the reason is fairly simple of why you need to take the LCM. We need to add 1 to itself 3 or a multiple of 3 times, and 2 to itself a multiple of 2 times in order to get 0. And so the smallest number that's both a multiple of 3 and a multiple of 2 is exactly the LCM. Here's a fact we might have seen before, that the order of a number a in Z mod n is n divided by the GCD of a and n. And the reasoning for that is, well, the order is some number, so that when you multiply that number by a, that's equivalent to adding a to itself that number of times. What we want to end up with is 0 mod n. In other words, we want to end up with a multiple of n in the integers. And if you think about it, using the prime factorizations, for example, of these numbers a and a, what you want is take n divided by the GCD of a and n. So as an example, the order of 8 in Z mod 12, or Z12, is 12 divided by the GCD of 8 and 12, and that's 4. So 12 divided by 4 is 3, and then we can check that. So we need to add 8 to itself 3 times, then only are we going to get 0 in Z mod 12. So 8 plus 8 is 16, and in mod 12, 16 is the same as 4. Okay, so we're not at 0 yet. 8 plus 8 plus 8, on the other hand, is 24, and in mod 12 land, 24 is same as 0. And so yeah, we've got that the order of 8 is 3. That's the number of times we had to add 8 to itself to get 0 in the group.